this one. So this is conversion of energy, but this time, because this person is jumping on the spring, so it involves she is moving up and down, so it involves gravitational potential energy. Earlier on, because the block is moving horizontally, so when it's moving horizontally, they are at the same horizontal level. So there's no change in gravitational potential energy. But this person jumping up and down, there is change in gravitational potential energy. Not only change in gravitational potential energy, but also kinetic energy, because when you reach the very top, the kinetic energy is zero. When you are somewhere at the equilibrium position, you are the fastest. Then after that, you have to compress the spring. So this problem involves all the three factors. Earlier on, not all the three factors involved, right? Okay, right. You read this problem 5.10.
A 50 kg circus acrobat drops from a height of 2 meters straight down onto a springboard with a force constant of 8 times 10 to the power 3 Newton, as in figure 5.23. By what maximum distance does she compress the spring?
Okay, right. So the key word here is, oh sorry, wait first. Okay. The key word here is drops. Drops. She is not jumping down. She just allow herself to fall freely, not jump down like that. Just uh, allow herself to fall freely. And this means that at the initial position, the velocity is zero because she allowed herself to drop down. Okay, drop down from a height of 2 meters. So that means at first she's at this position, v equals to 0, right? V equals to 0. Then she allowed herself to drop down 2 meters. This 2 meters is the h. This h is actually from her feet until the surface of the springboard. Okay, so this is h. So when she touches the springboard, the spring start to compress. So after compressing a distance of d, then she will come to a stop. So the question is, how much is this compression d here? So you understand the question or not?
Yes, sir.
Yes. So what we want to do is this person drop down, we want to calculate the potential energy, right? And this potential energy is converted into the spring potential energy. Because at first her velocity is zero. Finally, when the spring compress, she will come to a stop. Also, the final velocity also zero, right? So it is not that she has no kinetic energy. Along the way, she has kinetic energy, but at the initial position and the final position, she has no kinetic energy. That's all, right? So if that in that case, then the conversion is between gravitational potential energy and the spring potential energy. But you have to be careful because the gravitational potential energy is not just the height h, but also drop a further distance of d when you compress the spring. So the loss in potential energy is both the potential energy of the height and also the compression of the spring, because now the spring is vertical. When you compress the spring vertically, so the compression is also part of the height. The compression is also part of the height. So you have to include this, right? Okay. So now we come to this uh, energy equation. The energy equation is kinetic energy, potential energy, in the gravitational potential energy, spring potential energy, the total at the initial position is equal to the final kinetic energy, gravitational potential energy, spring energy at the final position. Because now there is no air resistance and we consider it's very small and negligible, right? So no air resistance. Okay, so the initial potential energy, the kinetic energy is zero because she dropped down. Initial potential energy, yes, she has. Initial spring energy, don't have because initially the spring is not compressed. Final kinetic energy, zero, because after compressing the spring, you come to a stop, zero. Final gravitational potential energy, zero, because we assume that the bottommost of the bottommost position is the zero position, so it's zero. Then at this position here, the spring is also compressed, so there is gravitational, there is spring potential energy. So now looking at this equation, we only have two numbers. First one, gravitational potential energy. Last one, spring potential energy. But the initial potential energy is mgy, m 50, g is 9.8, and the distance drop is this one, 2 meters plus d. 2 meter is this, 2 meter is the height between the acrobat and the spring platform. D is the distance compressed, and this distance compressed also has gravitational potential energy. That's why the D is there. And finally, the spring potential energy, half kx squared. Half k is 8,000. Oh, really? 8,000. Then the D is the compression of the spring, d squared. But it becomes a quadratic equation. When you rearrange the equation, it becomes a quadratic equation. So this quadratic equation, you have to solve using the formula. You have to solve using the formula. You reduce it to the form ax squared plus bx plus c. So the a is 1, the b is negative 0.123, and the c is negative 0.245. And solving this quadratic equation using the formula minus b plus or minus square root of b squared minus 4ac divided by 2a. So you take the numbers from here, substitute into the quadratic formula, and you have this distance is 0.56 meters. So what does that mean? It means that when this person dropped down from a height of 2 meters, the compression of the spring, at this position, the compression of the spring will be 5.60 meters. Any question?